Then first of all, a wonderful good morning and welcome to this installment of the software design track, a talk about type erasure. So my name is Klaus Iglberger and I work as a freelancing C++ trainer / consultant, and I usually talk about topics that are dear to me. And very often this is topics in the realm of software design, probably because this is a topic that few other people talk about. And so I also love talking about type erasure, which I personally find to be an absolutely amazing design pattern, something that I hope I can convince you about in this talk. I actually have talked about type erasure before. Last year at CppCon 2021, I talked about this as a design pattern, so a design analysis. In this talk, I actually tried to really show why this is such a fascinating thing, why it decouples so strongly, etc. However, in this talk, I'm not going to assume that you've seen this one, so I will do a quick recap and a quick introduction too. I want to dig deeper though, because last year I, on one slide, talked about all the advantages, including the point it improves your performance. But honestly, in the last year's talk, I did not really show how and why. And that's not now what I want to do. I want to go deeper, and I want to show you how you can improve the performance and what to expect. But most importantly, you should get an idea. All of this stuff is fairly simple. Sometimes it's just 10 lines of code, but it has amazing consequences, so positive consequences for your code. And so let's start by doing a quick motivation. This is just for getting you on the right page in case you have not heard about this before. So we have a function f down here at the bottom, and this function f is supposed to get some command. Again, kind of a design pattern, and this could be anything. This could be a print command, a search command, an execute command. Traditionally, we would have some kind of base class called command, which provides any operator or execute function that you just have to override in the deriving class. Would we do this today? No, seriously not. Today, we would definitely use a std function. And we'd use a std function for so many reasons. First, there's no inheritance hierarchies in this code. Yeah? And so it's non-intrusive. You can write your print command, your search command, or execute command without having to derive from any class. And so if you have a lot more freedom, a lot more flexibility, non-intrusive is always an absolutely amazing property of design. But there's also less dependencies. Usually, inheritance introduces dependencies, and this decouples very, very strongly. Yeah, as I said, you can implement your command in any way you like. Could be a lambda too. There's less pointers. So on your side, on your end, there is no pointers in this entire example. There's no manual dynamic allocation. You don't have to manually allocate, and so you don't have to manage the lifetime of something, which is so much simpler, so much nicer, because it's a value semantic solution. I talked about value semantics on Monday, and I really sold this as the thing, the one important property of modern C++. And then also there is just less code to write for you, which is definitely something that you probably like a lot. All right, this is what you know. Std function is kind of old. And okay, potentially better performance, yes. This is what you know. But yes, you can use this technique, this type erasure technique, for all kinds of problems. So let's consider my kind of go-to problem, a shape class with a pure virtual draw function, which you implement in many, many derived classes, circle, square, triangle, whatever. And the function f now takes a shape and does something with this shape. Now today I would also not do this. There's absolutely no need. I would write a type erasure wrapper. And that's exactly what we're going to do. And again, we have exactly the same advantages. No inheritance, non-intrusive, so circle, square, and triangle are much more independent, can be reused much more easily. Less dependencies, because, as you will see, circle, square, and the other shapes do not have to accumulate dependencies like draw or serialize or whatever operation you need on them. They're indeed so much simpler. No pointers, no manual allocation on your side, no lifetime management, value semantics again, and less code. And definitely I want to show you that you will get better performance, even if it's just a little bit, but it's definitely not worse. So this is exactly what we're going to do. We are implementing this shape wrapper. We're implementing this because, as Andrew Hunt, David Thomas said, inheritance is rarely the answer. The interesting thing about this quote is that the pragmatic programmers actually don't talk about C++. This is a book on all programming languages, general programming, and I believe they're absolutely correct. Also design patterns, even the classic ones, actually do not really benefit from inheritance, but mainly from, for instance, composition. But I believe that perhaps type erasure might be an answer, at least much more often. It depends. So let's take a look at a basic implementation, which is now a little similar to what I've done last year, but I will dig deeper, a little deeper at least in here too. But first, the terminology, because type erasure is a heavily overloaded term. Also in other programming languages, the term is used for many different things. In C++, we use it for a specific thing. So we do not use it for void pointers. Actually, this was used yesterday in one talk, and I said, no, please. No, it's not a void pointer. It's also not a pointer to base, and it definitely is not a variant. Definitely not. Please, never use it for this point, because from a design perspective, a variant is exactly at the other end of the design spectrum. And this would totally confuse people that have a little bit of an idea of software design. But type erasure is, and this is what I want to show you, definitely a templated constructor. You will definitely see a templated constructor. This is one of the primary ingredients. It has a completely non-virtual interface, and it is a mixture of a couple of design patterns. In particular, external polymorphism, the bridge, and the prototype design pattern. So now let's dig in, and let's start, I said, with this little toy problem of drawing shapes, which I know is a little boring, totally. And to say it in the words of my colleague from the user group, I'm tired of this example, but I do not know any better one. And that's my feeling too. It is a good example, and I hope it's simple, which means that hopefully you can focus on the structure. It's all about structure, it's all about dependencies, so ignore the drawing thing. So, here we go. I start simple with a circle class. And this is a class as you probably would expect of a circle. So the circle gets a radius, has a data member radius, probably a few more data members, of course, because there's probably some center point, perhaps some kind of rotation. And so there's also a couple of getter functions. But most important actually is what you do not see. So primarily, the square class, very simple, pretty much the same thing, just that it's a square. But what you do not see is that there is no base class. No base class at all. Will not need one. These are independent classes. This may be even from a third-party library that you cannot control, that you cannot change. You can directly use these classes if you want to. Also pretty important, they don't have to know about each other. Circle, square are totally independent. There is no connection whatsoever, no dependency whatsoever. And also super important, they don't know anything about any operation. They don't know about drawing, they don't know about serialization, rotation, translation. They are just totally oblivious of anything that you might want to do on them. And this is great because this is decoupling. But how do we get the behavior into circles and squares? So, for instance, drawing. Now, for that purpose, we start with an external hierarchy. And, well, because it's kind of a little bit of a tradition, I call this a shape concept. The shape concept is a classic base class with a virtual destructor, and that is exactly one deriving class. Or I should actually better say deriving classes, because what it's inheriting is a class template, shape model. Also, the name is a little bit of a tradition here. The shape model is a class template that takes a shape T and stores a shape T. So it acts as a wrapper around circles, squares, and all the other types that you might have and will have. So this is open for types. If you invent new ones, this will definitely still work. All right, in the base class, we now introduce the operations, also sometimes called affordances. So for the sake of this example, I have two, do serialize and do draw. This is the functions that I have to now implement in the shape model, and I do by overwriting them and implementing them as needed. I do not, though, directly implement drawing or serialization in this class, but I just forward to the function or class that does the work. So I forward the information in this first example by simply calling an according free function. So serialize and draw. So this is the real implementation, and this is now the real requirement. Any shape, circles, squares, etc., must implement a free draw and a free serialize function in order to count as a shape. And so it's the same kind of requirement that a base class usually gives you, where you have to implement this virtual function. But here it's the requirement you have to have this free function. Without this, it just would not compile. It would be compile time error. And that's just as a side note, note the do. The do is actually quite important in this context because else we would have a name lookup problem. So draw inside the class would look for a draw, and if the function itself is called draw2, this would be a mess. So I call it differently just to have a definitely better life. All right. This is the external polymorphism design pattern. So we create a separate hierarchy, a separate model for some independent types. And by that, I really isolate the operations pretty strongly. External polymorphism is a pattern that you might have seen before because it's not one of these classic Gang of Four patterns. The Gang of Four book was released in 1994. This paper is from 1996, so a few years after, but nonetheless, I believe this is a pattern that you should know about because it's absolutely fantastic and absolutely key for this type erasure idea. Okay, without going into too much detail, the external polymorphism design pattern allows any shape to be treated polymorphically. So circle, square, although there's no virtual function on them, we have added this externally. And it very effectively extracts implementation details. This is essentially what the single responsibility principle tells us to do. And it removes all the dependencies to operations. Circles do not know about drawing. They shouldn't. They should be simple. And this also creates an enormous opportunity for extension, both on the side of operations, but also, so not the kind of operation, but implementation of operation, but also on the side of adding new types of shapes. All right, so this is what we have. What I now add is the affordances. So serialize and draw for both circle and square. They just need to be available, else this would not work. Now, so these functions resolve the requirements. And of course, there can be many. This is not just one implementation of a draw or serialize. It depends on which header you include, for instance. It might also depend on which library you link. And it might depend on, also, we'll see this a little later, what you choose at runtime. So you have all the options. This is not just to have one implementation somewhere. Then draw all shapes. The next function is now a function that goes, well, over vector of different kinds of shapes. Pointers, it's pointers, and so I use unique pointers, of course, else a lot of people here would be very unhappy. And I traverse all of these shapes, and I simply draw them. And this will create some nice output, yeah, a nice visualization on the screen. This will definitely work fine. And in the main function, I, first of all, create a little bit of a shortcut. Standard vector of unique point of shape concept is quite a long name. So I call this shapes. I start with an empty vector, add a couple of shapes in form of a shape model, and then I draw. But this make unique is probably the most interesting part. I really create a shape model at this point. A shape model for circle, a shape model for square. This is where I put this into this wrapper. And all of these models are shape concepts that derive from that. This is why I can put them into this vector of shape concepts. Great, this works. It just doesn't leave you particularly satisfied yet. Because, to be honest, this looks classic. And with classic, I mean, it does look a little bit like this Gang of Four style from 1994. There's a lot of pointers. There is a lot of individual little allocations. And a lot of virtual functions, a lot of base classes floating around. It's not beautiful. So let's clean this up. Let's clean this up by actually moving towards the type erasure design pattern. And the primary idea is that I put all of this complexity into a wrapper. And this is what I call shape. The shape wrapper, now in the private part, contains these little two classes, the shape concept and the shape model. Just as we had them before, exactly in the same form. But then what I do add in the public section of this class is a constructor, a templated constructor that takes any kind of shape. Can take a circle, can take a square, a triangle, a rectangle, you name it. It can take any kind of shape and deduces the type. With this type, I now create the according shape model. Yeah, so the shape model of the given shape type. Of course, I move this shape into that model and initialize my data member called Pimple. So this is, again, a unique pointer of a shape concept. So if I have a circle, and if I put it in this constructor, then what this essentially does is it creates a model, instantiates this. Yeah, we create a model, give it to this pointer of shape concept, store it, and we've effectively erased the type. It's gone. All I now store is a pointer to base. And to this point, I really have no idea anymore what I got. Is it a circle? Is it a square? I have forgotten, kind of. Hence the name Type Erasure. Now, this templated constructor is super important and of course super convenient because it takes all the work of creating a shape model. You don't have to do this manually anymore. And it creates some kind of bridge, a bridge to some implementation details that the compiler generated, the model, and that is yet the other design pattern that I mentioned, that is the bridge design pattern. So it bridges to the implementation details that you don't really have to think about. All right, now I do add something that you might have seen before. I add a couple of friends. And I know, this is the sad part of this talk. You know that in C++ you should not have a lot of friends. Yeah, this is bad. It sounds bad, but these two friends, I believe, are good friends, real friends, friends that actually really help, because this now reflects the interface that we have on circles and squares too. So if we require a circle to have a free draw function, we want to have a free draw function also. But now you say, wait a second, this is inside the class. Oh, that's the funny part of this. This friend is a free function. It's not part of the class. I actually call this a hidden friend, because this is now injected into the surrounding namespace for exactly the shape that we have. So it doesn't have to be a friend. You could do it differently, but it turns out to be, I believe, the most reasonable design choice in this context. And these friends, these functions trigger the polymorphic behavior. They go to the Pimple, because they're allowed to. They call the doDraw or doSerialize functions, and this, of course, triggers the real behavior, the polymorphic behavior that we have implemented by means of the virtual functions inside the shape concept. And so, yeah, we might not really remember what we store, but we still, thanks to the virtual functions inside, have a way to go back and do the right thing, perfectly type safe and reasonably efficient. Okay, this is what I just said. All right, now, this is essentially what I said and talked about last time. Now I'm digging a little deeper because, of course, this is now some argument, but I would argue that we want to copy a shape. We want to copy a shape. Sounds reasonable. If you don't want to copy a shape, of course, the things that I now explain are kind of void, but we want to copy. Now, how do I copy? Because I actually don't know what I store. I don't know what I store, whether it's a circle or a square, and I cannot know. It's an open set of types. So we need a little more help. So a shape should be copyable, but we only know a pointer to base. There's one more function that we need, another affordance, and that I introduced by means of a clone function. Clone. I bet most of you have seen this before. This is another design pattern, a famous one, a gang of 4 design pattern, the prototype design pattern. So the clone function returns in a base class a unique pointer to a shape concept, but it's pure virtual. we have to implement it in the shape model, and we do return a copy, an exact copy of whatever is stored inside. Whether it's a circle or square, at this point we know for sure, and we can create the according model. Note that I use the copy constructor here. So even if we change something later, and we might, this will always do the right thing. So I'll never have to go back and update this in any way. So it's a little resilient to change. All right, so the copy operations are just implemented in terms of clone. The copy constructor just asks the other shape, could you give me a copy, please? Calls the clone function, and, well, we have one. We don't know what it is, but we don't really care. And a copy assignment operator is implemented in terms of the copy and swap idiom, which is kind of reasonable because, yeah, we need a copy anyway, so we use the copy constructor, and then we simply swap the pimples, and the old pimple is just going out of scope with this temporary shape. I know there is people that do not like copy and swap. It's so inefficient, but we need a copy anyway, so there is no better way. But if you want to, we can of course also write this in a single line. It's the same thing, but yeah, perhaps it's nicer. Perhaps you prefer this one. All right, then let's talk a little bit about the move operations, the last operations that we actually have to think about. And there's a couple of choices now. Design choices. What do we want our shapes to be? So the first option you have, and that's definitely the simplest one, is to default these two. That's simple. Because all we have as a data member is the pimple at the top of the slide. So if this is the only data member, by just defaulting the move operations, I actually can, well, make this movable. Great. However, there's a consequence. If you move from a shape, then basically you will have an empty shape. There's nothing inside this shape anymore. It's a null pointer. And perhaps this is surprising. Now you move from a shape and then suddenly it's gone. There's nothing and you cannot do anything on this anymore because, well, it's a null pointer. If you want that, your job is simple. But if you don't want that, it's a little awkward. It depends. So one example for something like this is, for instance, std function. Std function, if you move from that, is empty. Not really based on the standard. This is not a wording, but this is what you should probably assume. And there's a default function too. So if you create a new function, it's empty. And if you try to call it, it will just throw an exception. So if this is the behavior that you want, default the move operations. But if you do not want it to be empty, in case of a move operation, then what to do? Well, again, the simple choice is just to not write the move operations. Not write them. And note, I did not say delete them. This would be the wrong thing, because if you delete them and try to move, then you would get a compilation error. You would prevent the operation. But by getting rid of them, you actually really get rid of the move operation. There is none. And so as a replacement, you would do the copy. And it feels perhaps a little more natural, perhaps. However, again, there's a consequence, because of course, if you do that, then the move operations are not no except. They cannot be, because in the move operations, you would do an allocation as far as we are here. So yeah, that might be a little unexpected too. And so perhaps there is a mixture between the two. So there's an option 3. You can just not implement and not even mention the move constructor, so this would do a copy, but you can actually implement the move assignment operator with a no except. And you do this by simply swapping the pointers. Because as soon as we know for certain that all of the shapes will always have a valid unique pointer, a valid shape inside, we can actually swap these quite simply. And well, this is valid, but undefined, so this perfectly matches the behavior of a move assignment operator. But you have at least one of these operations as no except. So you see, it depends. It depends on what you want to have. It depends on what you want to express semantically. All right. There is no one solution. That's all I want to say. Now, draw all shapes. Once we have this shape wrapper, we would now have a draw all shapes again, which, however, now takes a vector of shape values. This is no longer a vector of pointers. And so it's nicer from a readability point of view, if nothing else. But we now have a vector of values. We would draw by means of this friend function that we've defined inside. And in order to call this, we simply have to create a couple of shapes. So shapes now is a vector of shape values. We create an empty vector and we put a couple of values inside. Now, at this point, all of you are absolutely amazed by the beauty. That is absolutely fascinating. Absolutely. There is no make unique anymore. There is no nothing weird. There's no pointers. It's super, super simple. So no pointers whatsoever. And of course, I mean on your side. I didn't say inside the shape wrapper. You don't have to manually allocate anything. And you don't have to manage any lifetime. There is never any question of ownership. It is a value. This is value semantics again. Great other example for this. You want to have something that is simple. And so I really feel this is so much simpler for the reader. Okay, let's agree. Inside the shape wrapper, there's a little bit of logic, but outside, beautiful. And so just to honor Kate and Guy a little bit, beautiful C++ indeed. Absolutely. All right. Now, there is a question about testability. How can I test that? How would I test that? And I should quickly address that because I feel testability is an enormously important aspect. What about testing? Well, actually, by using this, you've already improved testability quite significantly because you've separated concerns quite strongly already. So in a dependency graph, this is what it would look like. There is a couple of architectural boundaries now. There's two. And at the top, I have a high level, and at the bottom, I have a low level. And I apologize for these names. I know this is usually a little confusing. High level now, in my terminology, is the stuff that is more stable. More stable. So this is where the abstraction lives. This is where my shape wrapper is. Because this shape wrapper, this type erasure wrapper, does not contain any detail, does not contain any knowledge about a shape, circle, square, etc., and it does not contain any knowledge about how to implement an operation. It's just an abstraction. Below, I have circles and squares. And even below that, I now have the draw operations and serialize and all of this stuff. Very strongly separated already. And because of that, you actually can test this quite trivially. You can test the circle, if you want to, and you can test draw, if you want to, in isolation, totally separated. And you then later only bring them together by this wrapper. Pretty nice already. Very, very, very nice. But there's, of course, one more thing. It is working because of this shape model class. This is the code that brings it together. But this is the code that you don't have to maintain. This is the code that if you would have to maintain it, would be a little bit nasty. This is what you really would have to test, kind of. But no, it's generated. You don't have to deal with this logic. That's why this works so amazingly well. So this is the bridged code that is injected. But now let's, I know some people want to still inject some test code. So right now, honestly, we have hard-coded functions, draw, serialize, and all this stuff. What if I want to do it differently? For testing purposes or for other reasons, there may be many. What can I do to actually, say, inject other behavior? Oh, that's actually kind of simple. This is kind of simple indeed. Right now, in this model, well, there's nothing prepared for that, but let's just introduce another model. And we can, it's the private section of our class, nobody will notice. We add an extended model. And also this extended model is a concept. Note, type erasure, we don't remember. But now most importantly, this has another template parameter, a draw strategy. So this is the strategy design pattern. Perhaps in this form, better known as policy-based design. This is now the ability to just hold any implementation for drawing. And I just do this for draw. I think you can imagine how the serialized would look like too. We now have a new data member, draw strategy, which is just initialized via the constructor. We get a draw strategy, something. After all, it's a template parameter. And we just remember that. And when we want to draw, so here, we just call our drawer. And how do we inject this? Well, we inject this by simply having the according constructor. So this constructor takes any shape, but also any draw strategy. Anything that you like. We take them both, put them into an extended model. The extended model, again, is a concept, so we can assign this to Pimple, and we've erased the behavior. Yet again, we've erased the type, but we still have a point of injection, dependency injection. So this is now what you can exploit if you really want to, at runtime, decide, not really runtime, at compile time, decide what you want to have. After all, it's a template. And so, for instance, in the main function, if you wanted to, if you want to, you don't have to, you could, for instance, give a lambda, takes a circle and some drawing-related parameters, and implement drawing differently for testing purposes. Because of this strong decoupling, you can pretty much anything you like. This is the amazing beauty of this approach. All right. So amazing job so far. We have used Type Erasure to extract implementation details, as we're usually told to do, single responsibility, separation of concerns. We have an opportunity for easy extension. It is a fully open set of types. Anything you have that represents a shape can be added. There's no limit. We've also nicely separated interfaces. Let's don't stress this too much. We've reduced duplication and removed pretty much all dependencies to operations. Now, as I said, sometimes we call this affordances. Then there's no inheritance hierarchies left. There's no pointers left. There's no manual allocations left. And note, I said manual allocation. So we don't do this. Inside, it still happens right now. And we don't need to manual lifetime management. So, great. The only thing now is performance. Right now, it's a basic implementation. It's quite reasonable. This is also quite simply done, but, well, there is now potential for performance. So in order to give you an idea that this is not bad right now, let's take a look at the current performance values. Performance. Performance is critical. Critical in the sense of, with such a crowd, if you say anything about performance, there's at least 10 people that complain about the performance, about the setup, about this detail, about that detail. It would be an endless discussion. Therefore, let's just say that this is just some results on my system. And you promise me that you do not take these results too seriously. Do you promise that? Okay, so if you promise that I can really show you, I should explain a little bit what I'm doing, of course. So I now use 4 kinds of shapes: circles, squares, ellipses, and rectangles, which I feel is a little more realistic than just 2. I create randomly 10,000 shapes, so that doesn't have to be 2,500 of each, any number. And I perform 25,000 translate operations each. Translate means that I move the center point. Why do I do that? Because I want a very, very cheap operation. Super cheap, so cheap that you actually see any difference, if there would be. Any overhead created by, for instance, virtual function calls, etc. If I would have an expensive operation, this wouldn't really show. So something super simple. I benchmark with these 2 compilers. This is not a race between them, so please just consider this as some results. And this is the machine I'm using for that purpose. Okay, and here we go. The classic object-oriented solution that you would have, a classic implementation of a virtual draw member function, etc., this would run at that speed. A Type Erasure implementation, the thing that I've just shown you, runs at, yes, exactly the same speed. Which is not a big surprise, because after all, it's an inheritance hierarchy inside. There's one virtual function call, And indeed, just one, even if you inject some strategy, because after all, this is inside a template parameter. Quite nice, actually. It's exactly the same. So right now, we have just gained beauty. We have gained flexibility, and we actually follow the solid principles quite nicely. But now, let's deal with the optimization potentials. And the first optimization, performance optimization I want to show is actually a pretty important one. We call this a small buffer optimization. You've heard about something like this before. You commonly use something like this. You use the small string optimization, SSO. So in a string, up to a certain number of characters, the string does not allocate. So just use some number. So perhaps up to 16, say 15 perhaps characters can be stored directly inside the object because there's some space. But beyond that, we would have to dynamic allocate. Now, you know that a string is not limited in any way, so then it would just do a manual memory allocation. Now we do something like this. The only thing is that I now focus entirely on a small buffer and do not do any dynamic allocation. This is now the implementation that you can use if you cannot use dynamic allocations. If for whatever reason, new malloc, etc., is just not possible. So this is where we left. We had a constructor that says make unique, unconditionally, even for small things, which is seriously questionable, even for the most tiny shape we would call a new. All right, now what we change is we replace this by a buffer. This buffer is essentially a std array of bytes of some size. Now for simplicity, the size is just fixed here at 128 bytes, and the alignment is fixed to 16. So if you do something like this, please think about alignment. This is important. Do not ignore it. But right now, let's keep them as just a fixed thing. Now, so this class will only be able to store anything with 128 bytes. And if you have something that has at maximum a requirement of 16-byte alignment, this will work. So why std array? Because this will actually come quite handy. This is a copyable thing, so we exploit the fact that this is giving us some functionality. This is now the thing where we will store our object in directly by means of a placement new. But in order to get some address, in order to be able to work with that, I now provide a couple of functions with the name Pimple. So Pimple now becomes a function. And I know that this function looks seriously scary. Reinterpret cast. Yes, I know, this is the one thing that in a code review, people might ask questions about, but I actually talk to people, even according to the C++ standard, this is okay. So we know that we store an object of the according type inside this buffer. We know that. It has been created, and so getting back to that by means of this reinterpret cast is actually okay. So yes, I know, it's not beautiful, but unfortunately really required in this context. So, and I have two, one for the non-const, one for the const case. All right, now, again, this is the bridge design pattern. It is implemented differently now, but it definitely serves the same purpose. But now the constructor. It's again a templated constructor, and I got rid of the draw strategy again for simplicity reasons. I get some kind of shape, and I, first of all, shorten this a little bit. Model of shape T now is called M. And then I statically assert that the size of this model is not going to be bigger than what we specified, buffer size. It must not be. But beautifully, we can do this at compile time. We also check that the alignment is perfect. So if the alignment is smaller or equal the alignment, everything's fine. Otherwise, we would get a compilation error. And then we call a placement new. So call new is the global placement new. We give the address, that is what the Pimple does, and we construct a model with the according shape. So pretty much we do the same thing as before, just by, we use a different kind of memory. All right, then Shape concept and shape model are still there. It's exactly the same from a conceptual point of view as before. However, the implementation has changed a little bit to accommodate for this buffer. So, in particular, the clone function is now a little different. Clone does not return a new copy anymore, but I actually pass the memory location where I would like to have the copy. So please copy yourself here. In the model, this is now implemented again with a placement new. So we create a copy of the model exactly in the location that has been specified. So it's not complicated, it's just accommodating for this new piece of memory. You notice something new though, and again, it's the prototype design pattern. You notice something new though. One more side remark. Right, this might be interesting. Call new. So I specifically call the global placement new. And that's a good reason. There is people that sometimes have strange ideas. Of course it's not you, but perhaps your coworkers. And the class might actually have an overloaded placement new. Yeah, things happen. And in order to avoid that little problem, I specifically ask for the global one. Now, this is definitely much more likely the right thing that needs to happen. So, this is the thing that I started to talk about, move. There's a new function that actually provides move. Because move now is something that I cannot easily do anymore. I don't have a unique pointer anymore. This move operation now moves from the memory in this object to another memory. So pretty much what the copy did before. And the implementation is also pretty similar as the copy version. I just move the model to the other memory. Note, just to avoid misunderstandings, I do not move the memory. That is fixed. This is now this buffer. I move what's inside the memory. So if this is a circle or a square, there's not a lot I can do. This stuff will be copied. But if we would have a shape with something movable, something move-worthy, then this would be moved efficiently. All right, then we need a destructor. Yes, we do need a destructor because all we have is an array of bytes. The compiler wouldn't know what to destroy. It's not like a unique pointer that is calling the destructor, but it's just bytes. So we trigger the destruction explicitly by explicitly calling the destructor of our concept. It will do the same thing as before, but we just must not forget. This is a pretty important little detail. All right, then the copy operations. Again, I assume we want to copy, else you just avoid these. You don't have to implement them. But they're very simple or similar as before. We have this clone function, so we call it. We just pass the location we want to copy to be created. And in the copy assignment operator, again, I use copy and swap because it's simple. And in this context, I just swap the bytes, which is okay. If again, there's nothing weird going on in the according shape, so if there is references to self, for instance, this might be not okay. True, but we don't know the type. So it's type erasure after all, so there is a couple of things that you cannot really deal with. And then there's the move operations that pretty much work in the same way, except that we do not copy, but move. So we call this move operation, and we also move from the other shape by means of the move constructor instead of copy. So pretty similar, but definitely pretty nice from a performance perspective. We will see this shortly, but allow me to first talk quickly about this choice here. Of course, there's something that right now you don't like. It's fixed, so we cannot change this. And so, of course, we can talk about how to deal with this differently. And the first idea is obviously that we make this template parameters. So the shape class gets a couple of size t non-type template parameters, buffer size and alignment. There may be defaults, they don't have to be, and you are now able to specify these two from outside. Which, however, also now gives you probably a couple of ideas. Of course, we could go one step further and perhaps say that we could specify the behavior from outside. The way it deals with this, so we could make this a storage policy. Policy-based design again. So we can teach the shape how to deal with copy operations, which actually is possible, and this definitely gives you a lot of flexibility. So you could now have a dynamic storage thing, a stack storage thing, a hybrid storage thing. You can have a lot of different ways to deal with that. And you can, of course, equip your shapes with individual things, like here, the shape of dynamic storage. And you could have shape with a stack storage that perhaps can be assigned by shape 1. You could have a shape with hybrid storage. And of course, you could also think about how to assign these. However, and that's now a point I specifically make, it says requires special operation. So these operations are right now not implemented yet. Not implemented yet because this is different types. Every shape type is a different one. So this is not copy construction or move construction. This is different types. We would have to deal with all of these operations specifically. And how do I move from something that has static memory into something that has dynamic memory? Oh my, this is difficult. The problem is very, very similar to what we have in the standard library as well. If you consider a vector that has one allocator and another vector with a different allocator, this is actually really, really difficult. This is handled by the allocators, but it's not particularly easy. So for that reason, I believe this is just, for this talk, a little too deep. This would definitely be too deep. This is what you please do on your own. However, I think this is pretty reasonable anyway. Because, of course, you do remember what happens if you dig too deep. Yeah, we have seen this before. Of course. Yeah, you remember what happened to the dwarfs in Moria. Okay, but this is a different story. Please keep it simple. Yeah, keep it simple. If this is really required, that if a policy, then you have to deal with this. But this kind of destroys a little bit the idea that I want to give you. It's not difficult. It's actually pretty reasonable. All right, now the performance. Please do not expect too much. But note, I do create all of these shapes upfront and then use them. And by just using these static shapes, also static with shapes with static memory, I gain approximately 10% in performance. Now I say, okay, 10%. 10%! This is amazing. Yeah, you just with a little change in this class have actually gained 10% performance. You know what this means? You are employee of the month for several months. This is, I believe, seriously important. Definitely a significant improvement. And note, I said that I've created all the shapes up front. If you create your types very, very frequently, so on the fly, and you destroy them, create them, destroy them, create them, then of course the win would be so much bigger, because you do not have to allocate dynamic memory again and again. All right, so I believe this is a simple, a reasonable win, definitely, but there's one more thing that I want to show you. Manual virtual dispatch. Because there is one thing that is perhaps limiting in performance, and that is that so far we have always dealt with virtual functions inside. A nested hierarchy that uses traditional virtual functions, of course, there's something we can do. And now please do not believe that I suggest that we do this in a pretty weird and very low-level way. No, actually it will be quite reasonable indeed. But yeah, probably it's the toughest thing that I show you. But it's just approximately 10 lines of code, so bear with me. And I want to combine this, because the time is just short, with another little idea, which is that right now we actually might have another kind of overhead. So imagine we have some draw function that wants to take any shape, circles, squares, and right now would have exactly the right type. We would have the shape wrapper. So this function could take a shape reference, a constant reference to a shape. We could pass a circle, we could pass a square. This would compile, this would work amazingly. We don't have to add any base class, as I said all the time. But there's a disadvantage. Every time you now call this function with a square or a circle or anything else, you would create a shape on the fly. Now, depending on whether or not you use SBO or not, this might every time allocate a little bit of memory. By the way, this is also what is happening if you use a std function. A std function might allocate internally. And so for this kind of type erasure wrapper, this might actually be quite expensive. And so the idea now is that we create another abstraction. We create, instead of an owning abstraction that potentially allocates, we create a non-owning abstraction. And I call this to reflect the shape const ref from shape const ref. Perhaps another good name would be a shape view. You decide. Yeah, this is whatever you want to represent. So this is now the class that we write, the shape const ref. And as I said, I promise you, this is now a wrapper that neither allocates nor copies, but really represents a constant reference to a shape. And it is merely approximately, don't argue here, approximately 10 lines of code. So here we go. First of all, I do what every type erasure wrapper has. I add a constructor, a templated constructor that takes a shape_t const ref, just what I try to represent. Okay, and now you have to be strong, because now here comes the thing that looks horrible. I add a data member of type void pointer. A void pointer. This is the point where usually people leave the room and say, okay, this guy's nuts. But bear with me. I said this is fine. This is type safe. Everything's fine. Note, however, that I have at least a const. Yeah, a void const pointer. Beautiful. So in the constructor, I initialize my void pointer with the address of shape. Of course, this always works. Except, do you remember your colleagues? I know you, again, would never do that, but there is people that actually overload the address operator. Curious folk. For that reason, it might actually be an advantage to use std address off. So you avoid this problem altogether. You always will get the address to the shape, whatever the address operator does. And we now have a void pointer. Type erasure again. Seriously, type erasure. So far, we are not able anymore to get back. But here comes the solution. I first add a type alias. I call this draw operation. And the draw operation is an operation that takes a void const pointer and returns a void. And I add a data member called draw. That's my draw operation. And this is now a function pointer, as you see with a little asterisk, that I start to initialize with a null pointer. This is now my draw operation. And by the way, note, this draw operation could take more arguments again. It's the same idea as before. For simplicity, shorten a little. This is now initialized in the constructor in this way. So I initialize this with a function. But not just any function, I write a lambda. And you do remember that a stateless lambda can be converted into a function pointer. So this lambda I create on the fly, and I have to create it right here because this lambda still knows about the type, because it still is created in the constructor that knows the type, the real type, the shape t. So yes, the argument is a void pointer, but I know what it is. I know that it's actually a shape t thing. And so I cast back to a shape t const pointer, dereference that thing, and put it into the draw function, which again is the same draw function that we've seen before. So this is the affordance that we require. This thing needs to be drawable by a free draw function. That's it. But this draw function, we're now able to get back to the real type, do the real operation in a perfectly type-safe way. There's one thing missing. Something has to trigger this draw, and that's again what I do with a hidden friend. Again, it's called draw, takes a shape const ref, by reference to const, or just by value. It's a view after all. And you take the draw, take the shape, give it to the draw function, call it, and this will do the right thing. So this is the approximately 10, perhaps a few more lines of code that I promised. And I have to say, I personally feel this is absolutely astounding. This is absolutely amazing. This is a little drop-in abstraction that you can just write for anything. It's non-intrusive. You just add this on your own, anywhere you like. oh, here needs some shape. You write this little piece of code, and suddenly you have an abstraction from every possible shape that you can imagine. You never have any connection to that, so it's super loosely coupled. Absolutely great. From a design perspective, better than anything else I could suggest. Okay, but again, the performance numbers. Using the technique of storing these virtual functions as pointers inside the class. Of course, you can use this for all kinds of implementations. And this is now the idea that I use here. So on a benchmark, Type Erasure with this manual virtual dispatch, and the performance is quite good. Of course, it depends a little bit, GCC, Clang, whatever, but still, in comparison to the original call, it's quite amazing. Especially on GCC, Clang doesn't like it so much, but this may be just my implementation, my machine, etc. I don't know. It definitely, there's a good point. Now, of course, you're super curious about what happens if I combine these. Must be so much faster. Okay, not for me. For some reason, I did not really get this to be even better. But it's reasonable. So in other words, perhaps you have to make up your mind. Perhaps you try it. Perhaps you have a little more success than I do. I don't know. I did not really analyze this deeply. All right, so as a summary, Type Erasure is first a templated constructor plus a completely non-virtual interface. So everything virtual is kind of hidden. And it is a combination of a couple of very, very powerful design patterns. External polymorphism, bridge, and if you want copyability, also prototype. But I believe one of the most interesting design patterns today. But it achieves significantly reduced dependencies. That's why I would definitely reach for that. This is super important. It gives you value semantics, the real modern C++ form of doing things today. And it improves performance, improves readability and comprehensibility, of course not inside the class, outside, where it's so much simpler. Eases maintenance, for exactly that reason. And this is what I see, is for good reason the default choice for dynamic polymorphism in many other languages. So under the hood, you'll find this technique being used in a lot of other places. So I hope this was reasonable. I hope this could give you an idea what Type Erasure does. But of course, there's always more. There is always more. And you'll find a little more and I know this is a totally shameless pitch, in a book that I've written about this topic, about design, software design. A topic that I feel is totally underrepresented in the community. And so I now did the work and wrote a book of approximately 400 pages. One chapter is devoted to Type Erasure, but there's so much more inside, so much more design patterns, but also design principles. So hopefully this gives you a little bit of an idea how to properly structure software on a bigger scale. Okay, with that, I'm done. Thank you very much for the attention, and in case you have questions, please feel free to ask. Thank you. If you do have a question, please approach the mic. Yeah, please. Yeah, you're right.
Excellent talk, thank you. Is it possible to combine your first solution and the second one, like the stood string?
Absolutely.
Small buffer optimization?
Absolutely. This would just have been a little too much. So I tried to also, because I usually do training classes for embedded people too. They want to see the SPO-only solution. This is why I had this on the slide. But you can definitely combine this. Of course, it's a little more tricky,
right?
Of course, but I believe this is kind of the ultimate solution.
Okay, yeah. Great. Thank you.
So an online question.
Please.
What do you do if the external function needs private members of the class that don't have getters?
Correct. This is the usual problem that you have if you do not, so for all the design patterns that are externalized, there's nothing you can do. The question is it truly something so secret that I cannot reveal it? If it is, okay, then perhaps this is something that you cannot do. You cannot so strongly separate concerns. But I would suggest think about how to separate these things that you can actually make this work too. But no, if you need private properties, cannot be used. Please.
Hi, thanks for the talk. If you have a closed set of types, and you wanted to regain your value semantics for dependency injection, do you think concepts would be a more appropriate technique?
So this is dynamic polymorphism, and it is an open set of types. So if you now give me what you say, then yes, absolutely. But stating if you want a closed set of types, but still dynamic polymorphism, the right solution is a variant. This is the thing at the other end of the spectrum. I mentioned this shortly at the beginning of the talk. I said type erasure is not a variant because exactly for that reason. One is a closed set of types. This is an open set of types. Thank you. All right. Thank you very much.